Say the word nuclear and watch what happens. In a room full of people, some will think of the bomb. Some will think of Chernobyl. Some will think of a glowing green substance from a cartoon. Some will think of clean energy. Some will think of cancer. Some will think of the sun. They are all correct, and almost all of them are thinking about it wrong. Nuclear energy is, at this moment, one of the most politically charged topics in the world. It is also one of the most misunderstood. The word itself carries a weight of association, fear, power, catastrophe, secrecy, that makes it almost impossible to have a calm conversation about what it actually is, where it comes from, what it has done, what it has not done, and what role it might play in the future of a civilization trying to power itself without destroying the climate. This episode is going to try to have that conversation. Not as advocacy, not as reassurance, not as alarm, as history. Because the story of nuclear energy, where it came from, who discovered it, who received credit and who didn't, what the technology actually does and how, what the accidents actually were and how they happened, and what the record of the past 70 years actually shows. That story is far more interesting, far more complicated, and far more relevant than most people realize. And it begins, as so many things in this series begin, with a woman whose name you should know and probably don't. To understand nuclear energy, you first have to understand what it is and where it comes from. Every atom consists of a nucleus, a tiny, dense core made of protons and neutrons, surrounded by a cloud of electrons. The nucleus is unimaginably small. If an atom were the size of a football stadium, the nucleus would be the size of a pea at the center. And yet, it contains almost all the atom's mass. The protons and neutrons in the nucleus are held together by what physicists call the strong nuclear force, one of the four fundamental forces of nature. The strong force is, as its name implies, extraordinarily powerful. It has to be, because the protons in the nucleus are all positively charged, and like charges, repel each other with enormous electromagnetic force. Without something stronger to hold them together, every nucleus with more than one proton would instantly fly apart. The strong nuclear force provides that something. It acts only at very short range, within the nucleus, but within that range, it is vastly stronger than electromagnetism. The key insight of nuclear physics, the one that makes nuclear energy possible, is that the binding energy of a nucleus is not simply the sum of its parts. When protons and neutrons are bound together in a nucleus, the resulting nucleus has slightly less mass than the sum of its constituents. The missing mass has been converted into binding energy in accordance with Einstein's famous equation E equals mc squared. This binding energy is what nuclear reactions release. In fission, splitting heavy atomic nuclei, the products have more binding energy per nucleon than the original nucleus. The difference in energy is released. In fusion, combining light atomic nuclei, the product has more binding energy per nucleon than the starting materials. Again, the difference is released. The amount of energy involved is enormous. A kilogram of uranium fuel undergoing fission releases roughly 3 million times as much energy as a kilogram of coal undergoing combustion. The same mass of fuel, 3 million times the energy. This is why nuclear energy is simultaneously so promising and so dangerous. The concentration of power is extraordinary. In December 1938, two chemists were working in a laboratory in Berlin. One of them was Otto Hahn, a German chemist, meticulous and respected, one of the leading figures in radiochemistry. The other was his assistant, Fritz Strassmann. They had been bombarding uranium with neutrons, following up on experiments that had been going on across Europe and America for several years, sparked by the discovery of the neutron by James Chadwick in 1932 and the development of the first particle accelerators. Physicists were exploring what happened when you fired particles at atomic nuclei. What Hahn and Strassmann found in December 1938 was something that made no sense under the prevailing understanding of nuclear physics. When uranium was bombarded with neutrons, one of the products appeared to be barium, an element with roughly half the atomic mass of uranium. This should have been impossible. Previous experiments had found elements close in mass to uranium in the products of neutron bombardment. Knocking small pieces off a heavy nucleus was conceivable. Splitting it nearly in half was not. Hahn was confused. He trusted his chemistry. The barium result was chemically unambiguous, but he did not understand what it meant physically. He was a chemist, not a physicist. He wrote a letter, not to a colleague in Berlin, to a colleague who was no longer in Germany, who had been forced to flee 8 months earlier when the Nazis implemented laws barring Jews from government positions, including university professorships. He wrote to Lisa Meitner. Lisa Meitner was born in Vienna in 1878, the third of 8 children of a Jewish family. She was one of the first women to earn a doctorate in physics from the University of Vienna in 1906, at a time when women were barely admitted to universities at all and almost never allowed into scientific laboratories. She moved to Berlin to work with the physicist Max Planck, who initially questioned whether women should be allowed in physics lectures, then relented, then became one of her strongest advocates. She began collaborating with Otto Hahn in 1907. They worked together for 30 years. It was not an equal collaboration in the sense that the world recognized. For the first years, Meitner was not allowed in the Institute's main building because she was a woman. She worked in a converted basement carpentry shop. She received no salary. She was listed on papers, when she was listed at all, in ways that understated her contributions. But the science she did was real and important and recognized by her colleagues, if not always by the institutions. By the 1930s, Meitner was one of the leading nuclear physicists in the world, a fact acknowledged by Einstein, who called her our Marie Curie. She headed the physics section of the Kaiser Wilhelm Institute for Chemistry in Berlin. She had a reputation, an international network, and decades of expertise in exactly the area that would prove crucial to understanding what Hahn had found. In March 1938, Nazi Germany annexed Austria. Meitner, who had held Austrian citizenship and had therefore been somewhat protected from the anti-Jewish laws that had been in force in Germany since 1933, was suddenly exposed. She was a German Jew under Nazi law in a country that was stripping Jews of their rights, their positions, and increasingly, their safety. In July 1938, with the help of colleagues, and with a diamond ring provided by Otto Hahn that could be sold if needed to bribe border guards, she fled Germany to the Netherlands. She eventually settled in Sweden, at the Nobel Institute in Stockholm, where she continued her research. She was 60 years old. She had left behind her life's work, her laboratory, her books, most of her possessions, and the collaboration of 30 years. When Hahn's letter arrived in December 1938, Meitner was visiting a colleague in the Swedish town of Kungälv. Her nephew, Otto Robert Frisch, also a physicist who had fled Nazi Germany and was working in Copenhagen, happened to be visiting her for the Christmas holiday. They went for a walk in the snow. They sat on a log. And on that log, in that snow, Lisa Meitner and Otto Frisch worked out what Hahn had found. Meitner had something Hahn lacked: a theoretical framework for understanding what the chemistry was telling him. She was familiar with the liquid drop model of the nucleus, the idea, developed by the Danish physicist Niels Bohr, that the atomic nucleus behaved in some ways like a drop of liquid, with a surface tension that held it together. A neutron entering a uranium nucleus would cause it to oscillate. If the oscillation were violent enough, the nucleus might elongate, deform, and split into two smaller nuclei. She did the calculation on the spot. If uranium-235 split into barium and krypton, which was consistent with Hahn's chemistry, what would the mass balance be? She calculated the masses of the products. She compared them to the mass of the original uranium nucleus. There was a discrepancy. Mass had been lost. Using Einstein's E equals mc squared, she calculated how much energy that mass corresponded to. The answer was approximately 200 million electron volts per fission event, an enormous amount of energy, far larger than any chemical reaction, consistent with what the liquid drop model would predict for the splitting of a uranium nucleus. Meitner and Frisch had understood what Hahn had observed. The uranium nucleus had split in two. It had not been chipped, it had been halved. And in the process of splitting, it had released an extraordinary amount of energy. They coined the term for it, fission, from the Latin word for splitting. Frisch returned to Copenhagen and told Niels Bohr. Bohr was boarding a ship to America. He arrived in New York in January 1939, and within days, the news had spread through the American physics community. When Hahn and Strassmann published their chemical results in January 1939, they did not include Meitner's name. Meitner and Frisch published their physical interpretations separately later in January. The two papers together, the chemistry and the physics, constituted the complete discovery of nuclear fission. The Nobel Prize in Chemistry was awarded in 1944 to Otto Hahn alone. Lise Meitner was not mentioned. She was nominated for the Nobel Prize multiple times. She never received it. The element meitnerium, number 109 on the periodic table, was named after her in 1997, 59 years after the discovery on the log in the snow. Her colleague Hahn, who had written to her for help understanding his own results, received the prize. She received an element. This is the pattern. You have seen it before in this series. You will see it again. The discovery of fission, announced in January 1939, confirmed within weeks in laboratories across Europe and America, immediately raised a question that everyone in physics understood simultaneously. Fission releases energy. It also releases neutrons. Those neutrons can trigger fission in other uranium nuclei. Those fissions release more neutrons. A chain reaction. A controlled chain reaction in which the rate of fission was managed to produce steady, usable heat. That was a reactor, a weapons application. An uncontrolled chain reaction in which fission multiplied exponentially within microseconds. That was a bomb. Both possibilities were obvious. Both were pursued. And the political context of 1939, Nazi Germany in possession of some of the world's best physicists, war beginning in Europe, meant that the weapons application received the most urgent attention. The Manhattan Project, the American program to develop nuclear weapons during World War II, brought together an extraordinary concentration of scientific talent in facilities across the United States, primarily at Los Alamos, New Mexico, Oak Ridge, Tennessee, and Hanford, Washington. The scientific director was J. Robert Oppenheimer. The participants included Enrico Fermi, who had demonstrated the first controlled nuclear chain reaction in Chicago in December 1942, and dozens of the most eminent physicists of the era, including many who had fled Europe. Lise Meitner, the person whose theoretical work had explained fission, was not invited to participate in the Manhattan Project. She declined to participate in weapons development in any case, but she was not asked. The bombs dropped on Hiroshima on August 6, 1945, and Nagasaki on August 9, 1945, killed between 130,000 and 226,000 people in the immediate explosions and the acute radiation effects that followed, with additional deaths from radiation-related illness in subsequent years. Meitner in Sweden heard the news. She was distressed and reportedly wept. She gave an interview to a New York City radio station from Sweden saying, "I myself have not in any way worked on the smashing of the atom with the idea of producing death-dealing weapons. You must not blame us scientists for the use to which war technicians have put our discoveries." The discovery she was referring to was hers. After the war, the same technology that had produced the bomb was directed toward the production of electricity. The first nuclear power station to produce electricity for a public grid was the Obninsk nuclear power plant in the Soviet Union, which began operation in June 1954. The first commercial nuclear power station in the United States was Shippingport, Pennsylvania, which opened in December 1958. The principle of a nuclear power station is, at its core, simple. Uranium fuel undergoes controlled fission in a reactor core. The heat produced heats water, producing steam. The steam drives a turbine. The turbine generates electricity. The nuclear reactor is, in this sense, a very expensive and very sophisticated way to boil water. The complexity and the cost and the risk lies in controlling the chain reaction, managing the heat, containing the radioactive materials, and disposing of the waste. Through the 1950s and 1960s, nuclear power expanded rapidly in the United States, Britain, France, the Soviet Union, and other industrialized countries. The energy density of nuclear fuel, the ability of a small quantity of material to produce enormous amounts of electricity, made it enormously attractive. The promise of electricity, too cheap to meter, in the phrase of Atomic Energy Commission Chairman Lewis Strauss in 1954, captured a genuine enthusiasm for what seemed like a transformative technology. By the early 1970s, nuclear power was producing significant fractions of electricity in several countries. France, in particular, built an ambitious nuclear program that by the 1980s was providing 70 to 80% of the country's electricity, a fraction that remains roughly accurate today. And then came the accidents. On March 28, 1979, a partial nuclear meltdown occurred at the 3 Mile Island Generating Station in Pennsylvania. A combination of equipment malfunction and operator error led to a loss of coolant in the reactor core. Part of the core overheated and melted. Radioactive gases were released into the containment building. A small amount of radioactive gas was released to the environment. The accident terrified the public. It happened 12 days after the release of a film called The China Syndrome, about a fictional nuclear accident, which had used the phrase, "an area the size of Pennsylvania," to describe the potential contamination zone. The coincidence of fiction and reality, the film still in theaters as a real nuclear accident unfolded in Pennsylvania, was devastating for public perception of nuclear power. The health effects of 3 Mile Island, as studied by multiple independent investigations, were minor. The radiation released was small, comparable in the estimates of public health researchers to the radiation dose from a single chest X-ray for people living within 10 miles of the plant. No deaths or injuries have been conclusively attributed to the accident, but the psychological and political effects were enormous. Public opposition to nuclear power increased dramatically. No new nuclear power plant was ordered in the United States after 1978, and no new plants came online after 1996. The American nuclear industry effectively stopped expanding. The accident had demonstrated that nuclear reactors could fail in unexpected ways, that human factors played a crucial role in safety, and that the consequences of a serious accident, even one that caused no deaths, were politically and economically devastating. On April 26, 1986, at the Chernobyl nuclear power plant in what is now Ukraine, one of the reactor cores exploded. This was not like 3 Mile Island. This was a catastrophic failure. The reactor involved, a Soviet-designed RBMK type, had a design flaw that made it unstable at low power levels. Under certain conditions, a loss of coolant would cause the reaction rate to increase rather than decrease. This is called a positive void coefficient, and it is a property that Western light water reactors, which become less reactive when coolant is lost, do not share. During a safety test, operators violated several safety procedures and drove the reactor into an unstable condition. When a control rod insertion was attempted, a power surge occurred so rapidly that the reactor was destroyed by steam explosions before the control rods could have any effect. The graphite moderator, another feature absent from Western reactor designs, caught fire, burning for 10 days and spreading radioactive material across a large area. 2 workers died in the immediate explosion. 28 emergency workers, the first responders who fought the fire, died from acute radiation syndrome in the weeks following the accident. This is the direct death toll that is clearly attributable to Chernobyl. The longer-term health effects are more contested and more complex. The most studied consequence is thyroid cancer, particularly in children who consumed contaminated milk in the affected areas in the days after the accident, before authorities warned people not to. An estimated 6,000 cases of thyroid cancer have been attributed to Chernobyl. Thyroid cancer, caught early, is highly treatable. The mortality rate from these cases has been relatively low. Approximately 15 deaths from thyroid cancer have been definitively attributed to Chernobyl exposure. There are also elevated rates of other cancers in the most heavily exposed populations, the emergency workers, and the most contaminated communities. The precise numbers are difficult to establish because the background rate of cancer in the Soviet Union and its successor states was already poorly documented, and the populations were exposed to multiple risk factors simultaneously. Estimates of total deaths attributable to Chernobyl range from dozens to tens of thousands, depending on methodology and assumptions. The UNSCEAR, the United Nations Scientific Committee on the Effects of Atomic Radiation, estimated approximately 4,000 total cancer deaths from Chernobyl exposure over the lifetimes of the exposed populations. The exclusion zone around Chernobyl remains uninhabited by humans, but has become, paradoxically, one of the most wildlife-rich areas in Europe. Without human activity, the ecosystem has recovered in ways that the radiation has not prevented. On March 11, 2011, a magnitude 9.0 earthquake struck off the coast of Japan, producing a tsunami that killed nearly 16,000 people. The Fukushima Daiichi nuclear power station was struck by the tsunami. The wave exceeded the height of the plant's seawall. Backup diesel generators, which were needed to pump cooling water through the reactors, after the earthquake had shut them down, were flooded and disabled. 3 reactor cores melted down over the following days. Hydrogen explosions damaged the reactor buildings. Radioactive material was released. The direct health effects of Fukushima, by the most careful epidemiological studies conducted since, have been remarkably limited. No deaths have been directly attributed to radiation from the accident. One worker died of lung cancer in 2018 and received official recognition as a radiation-related death, a single case. The scientific consensus, as of the best available studies, is that radiation exposure at Fukushima caused no detectable increase in cancer deaths in the general population. The evacuation of approximately 154,000 people from the area around the plant, conducted rapidly, in winter, involving many elderly and infirm people, caused a significant number of deaths from stress, exposure, and disrupted care. Estimates range from 1,000 to 2,000 deaths attributable to the evacuation itself rather than to radiation. The psychological effects of Fukushima were severe and documented. Residents of the evacuation zone reported high levels of depression, anxiety, and community disruption. Suicide rates increased in some groups. The long-term economic and social costs of the displacement were enormous. Japan shut down all of its nuclear power plants following the accident. The electricity gap was filled primarily by coal and gas. The resulting increase in fossil fuel combustion and the air pollution it caused has been estimated to have caused more deaths per year than Chernobyl and Fukushima combined. This is not an argument that nuclear is safe. It is a statement about the comparative risks of different energy sources, and it is a statement that deserves to be made precisely. Let me try to present the safety record of nuclear power as clearly and fairly as possible. Every energy source causes deaths. Coal mines collapse, oil rigs explode, natural gas pipelines leak. Wind turbines have maintenance workers fall from them. Hydroelectric dams fail catastrophically. The relevant comparison is not between nuclear power and perfection, but between nuclear power and the alternatives. The standard metric for comparing energy safety is deaths per unit of energy produced, deaths per terawatt-hour, or deaths per trillion watt-hours. By this metric, coal is the most dangerous energy source in common use, producing an estimated 24.6 deaths per terawatt-hour in the global average, largely from air pollution and mining accidents. Natural gas causes 2.8 deaths per terawatt-hour. Oil causes 18.4. Solar causes 0.02. Wind causes 0.04. Nuclear power, including the deaths from Chernobyl, Fukushima, and all other nuclear accidents, causes approximately 0.07 deaths per terawatt-hour. Nuclear power is, by this measure, one of the safest energy sources ever deployed at scale, safer than coal by a factor of more than 300, safer than natural gas by a factor of 40. This finding is not a secret or a piece of pro-nuclear advocacy. It is the result of careful epidemiological and public health research conducted by institutions including the WHO, the UNSCEAR, and academic research groups with no particular stake in the nuclear industry. It is also not a complete picture. The deaths per terawatt-hour metric does not capture the fear and displacement caused by nuclear accidents, the unresolved problem of radioactive waste storage, the catastrophic potential of a worst-case accident in a densely populated area, or the proliferation risks associated with the technology's connection to weapons. These concerns are real. They do not disappear because the death statistics are what they are. The most genuinely difficult, unsolved problem in nuclear energy is not safety. It is waste. Nuclear fission produces radioactive waste, materials that emit ionizing radiation for periods ranging from decades to hundreds of thousands of years. High-level nuclear waste, spent fuel rods from reactors, is intensely radioactive and must be isolated from the environment for long periods. The challenge of storing this material safely for geologic timescales is one that no country has yet fully solved. Finland is the furthest along, with a deep geological repository under construction at Olkiluoto, a facility designed to store spent nuclear fuel in stable rock formations for 100,000 years. Sweden and France have similar projects at various stages of planning and construction. The United States proposed the repository at Yucca Mountain, Nevada, which was extensively studied and then cancelled in 2010 due to political opposition. The waste from American nuclear plants is currently stored in dry casks at the sites of the plants themselves, a solution that works in the short term and is not a permanent answer. This is a real problem. It deserves honesty about its difficulty and about the fact that it has not been solved. Critics of nuclear power are right to raise it, but the waste problem should be placed in context. The total volume of high-level nuclear waste produced by all the nuclear power stations in the world since the technology began is surprisingly small. The entire world's high-level nuclear waste, if consolidated, would fit inside a structure the size of a large warehouse. By contrast, the waste products of fossil fuel combustion, carbon dioxide, methane, particulates, are released directly into the atmosphere in quantities of billions of tons per year, with consequences that are reshaping the Earth's climate. Both waste streams are serious problems. They are not comparable in scale. The climate context is where the debate about nuclear energy has arrived in the 21st century. Decarbonizing electricity generation, replacing coal and gas with sources that do not emit greenhouse gases, is widely recognized as essential to limiting climate change. The low-carbon electricity sources available at scale are solar, wind, hydroelectric, and nuclear. All of them have costs, limitations, and challenges. None of them is a perfect solution. Nuclear power generates electricity continuously, regardless of weather, unlike solar and wind, which generate intermittently. It has a small land footprint relative to its energy output. It produces no greenhouse gas emissions during operation. Its safety record, despite 3 high-profile accidents, is better than most fossil fuel alternatives on a deaths-per-energy basis. Several countries, France, Sweden, Switzerland, have shown that it is possible to power a modern economy with a large fraction of nuclear electricity at low carbon emissions and reasonably competitive cost. Several countries, Germany, Belgium, have decided to phase it out and are grappling with the consequences for their energy mix and their emissions. The debate is ongoing. The answer is not obvious. Anyone who tells you it is obvious is not paying attention to the full complexity of the question. There is an element on the periodic table called meitnerium. It is element number 109. It is a synthetic element. It does not occur naturally and can only be produced in particle accelerators in quantities of a few atoms at a time, lasting for fractions of a second before decaying. It is named for Lisa Meitner, the physicist who explained nuclear fission on a log in the snow in Sweden in December 1938, who fled Nazi Germany with a diamond ring in her pocket, who spent the war in Stockholm, who wept when she heard what had been done with the discovery and who never received the Nobel Prize that most of her contemporaries believed she deserved. She lived to 90 years old. She outlived Otto Hahn. She saw nuclear power stations producing electricity. She saw the weapons that the discovery had made possible used against civilian populations. She gave lectures, received honors, and continued working until she was past 80. She said, late in her life, that she had never lost her love of physics, even in the years when physics had been used for destruction. The force inside the atom, the energy locked in the nucleus by the strong nuclear force, released by fission and fusion, the energy that powers the sun and the stars, the energy that can boil water and generate electricity and also level cities. That force was not discovered by the people who built the bombs or the reactors. It was discovered by a woman on a walk in the snow. It was explained by the mathematics she had spent a lifetime building. It was named by her nephew, standing beside her in the moment the understanding arrived. Nuclear energy is not one thing. It is not the bomb, and it is not perfectly clean electricity, and it is not Chernobyl, and it is not the sun. It is a physical reality, a consequence of the structure of matter, the binding energy of nuclei, the equation that connects mass to energy. It was always there, in every atom of uranium and plutonium and hydrogen in the universe. Human beings found it in the early decades of the 20th century through a remarkable convergence of theoretical physics and experimental chemistry. And then they had to decide what to do with it. They are still deciding. In the meantime, the force inside the atom runs 82 nuclear reactors in 30 countries, providing about 10% of the world's electricity. In France, it provides 70%. In Sweden, about 40%. In the United States, about 20%. The reactors are boiling water. The water is making steam. The steam is turning turbines. The turbines are generating electricity. The discovery that made this possible was made on a log in a Swedish forest on a December day in 1938 by a woman whose name you now know.